Thank you very much for the kind introduction, and thank you very much for the opportunity to speak here today. As said already, I'm talking about the nanospray drying of RNA encapsulating LNPs, and I want to start off with the why. Why is this interesting? Why should anyone work on that? I think we can all agree that RNA is a very potent class of new APIs that we can use for an array of diseases where we were not able to treat before because we couldn't reach the target that we wanted to treat or where we wanted to prevent. And especially in the lung, there are a lot of diseases, from inflammatory to even lung cancer or different other diseases we can have here, where RNA would really be beneficial for the treatment. While RNA can mean a lot of different molecule types, I'll be talking about siRNA today. And while siRNA is quite small for an RNA, it's still rather large and hydrophilic, so it will not enter the cell by itself. And also it's prone to hydrolysis and enzymatic degradation. And one way to overcome that is to pack the RNA into lipid nanoparticles, and then they can stabilize the RNA and they can bring this inside the cell, However, we also all know LNPs, and we know that there are issues with the storability, there are issues with transportation, and also if you want to get some kind of treatment from LNPs, you have to see a doctor and he or she will inject you with something. So this is not ideal. And one way to overcome all of these challenges would be to spray dry those. In my case, to nanospray dry, and I will explain you shortly what nanospray dry means here. But overall, if we add a matrix formulation and dry the powders, then we can make inhalable treatments, which would be especially beneficial if we want to treat something in the lung. And also the powder will be more stable than the liquid form. In the end, we would have nano-embedded microparticles, and if you inhale those, the matrix should melt away, should dissolve away, and the LNP will be free again and enter the cell, facilitate endosomal escape, and the RNA will be set free where it should be and can do the gene silencing that we intended it for. Now I've said that I'm doing nanospray drying. What does this mean? I have brought you the conventional spray drying process, and I'm sure you all know how it works, but just very quickly, you have a liquid feed that will be pumped into an atomizer. In this case, this is a spray nozzle. You will then have fine droplets at hot drying gas, and the liquid will evaporate. In the end, you have dry particles that can be collected via a cyclone. For nanospray drying, you also have a liquid feed that is pumped into an atomizer. However, in this case, it's a nebulizer. And this means that the particles can be a lot smaller, or the droplets can be a lot smaller than in a conventional spray dryer. And for this reason, you can have laminar airflow and you can have cooler drying gases. However, if you have smaller droplets, you will also have smaller particles in the end. It's harder to catch those in a cyclone. So in the case of the nanospray dryer we use, they use a collector electrode. So the particles will enter an electrical field and will be drawn to the electrode on the outside, and you scrape the powder off by hand. If you want to establish a nanospray drying process, there are a lot of things you have to think about, but there are 3 things I want you to focus on today. And this is the pumping and nebulization, the formulation, and the temperature. Let's start with the nebulization part. The nanospray dryer uses vibrating mesh nebulization. You have a liquid feed on top or in front of a mesh, and this will be actually activated by a piezoelectric crystal. It will vibrate and thus rip out droplets from the feed. This is not something that is only inside of the nanospray dryer, but actually also commercialized in an array of different nebulizers like the Aerogen Pro or the Power eFlow-Rapid. And in the past, we have seen that LNPs can be nebulized, but this can also pose some issues. So there is a previous project that I worked on where we tried to nebulize siRNA LNPs with these different nebulizers. And I don't want you to focus on every single point here. I just want you to see it as groups. You always see at first, the first column is always the non-nebulized particles, and then you have the pari and the origin-nebulized particles. And you see that for every group, no matter what kind of dispersant or concentration we used, the size would go up a lot. And we also saw that we have partial RNA release. However, most importantly, if you have a look at the in vitro data here, I'm not entirely sure how to do this, but on the right, you can see that you have a reduction of expression in the cell if you add non-nebulized as well as if you add nebulized particles. So while we have some aggregation and we also have RNA release, in the end, they still work. So we knew when we started with the nano spray drying process formulation and optimization that we had to do something about the shear stress, but we also knew that we probably could make it work. The first thing I did was find out the right vibration frequency, and this happens to be 110 kilohertz for this device. Then we wanted to have the lowest spray rate possible because we knew that the more we sprayed or nebulized at the same time, the harder this is for the LNPs. On the other hand, we still have to form some kind of droplets, so we can't go too low. And also, we don't want to cycle our LNPs. So this device is made in a way that you will pump the feed inside the head, and then only part of it will be nebulized. And then the rest will be pumped back into the feed again and pumped inside the head again. And this cycling really poses too much shear stress on LNPs. And we see that they aggregate a lot and they don't work anymore. So I really had to tweak the pump rate with the nebulizing rate to really have almost everything nebulized at the first attempt. And as you can see, above you can again see the size, down you can see how they performed in vitro. The pumping, in the end, really wasn't an issue anymore. The last thing we had to think about was the pore size. And for this device, we have different pore sizes available. If you have a look at the nebulized particles, nebulized with a medium-sized pores, then you see that the size increases a lot, and also we lose a lot of function in the cells. However, if we use the larger mesh, we can see that there is not a lot of size increase, and they work pretty well. So the nebulization we have optimized, and this works quite okay. The next thing I did was reduce the temperature. How low of a temperature can I use to still produce a powder that I can retrieve? And I did this with mannitol because we had quite some good previous experiments with that. And in fact, I could go down to room temperature with my nanospray drying here and still retrieve a powder that I could scrape off and that I could analyze. And you can see that, for example, for the residual moisture, it doesn't matter how hot the air is that it dries it, and it also doesn't really matter if we add LNPs, the residual moisture is still quite low. So here's where I thought, okay, we have the nebulization down, we have very low temperature, this has to work, and I nanospray dried, and actually it didn't work. We have a huge size increase, as you can see on the left, and the performance in vitro is not very good. The knockdown is only about 60%, and I've repeated this experiment quite sometimes, it doesn't really get better. So what else is there that is happening to the LNPs? And one actually quite obvious thing is the drying itself, because we don't only nebulize and then heat treat these things, we also take away the water that actually also stabilizes our particles. And if I want to dry particles without adding any shear stress or heat, I can lyophilize them, and this is what I did. And you can see that I use different formulations to find out what impact of the drying formulation I have. And for lactose, trehalose, and mannitol, we see quite some size increase. And also we see that for lactose and trehalose, our particles still work quite well. But for mannitol, they don't. And why is that? And again, I don't want you to focus on the individual points. I want you to focus on the shape of the curves. These are XRD data of lyophilized lactose and trehalose, where you can see that there's a really nice and smooth curve. So these dry amorphously. And the mannitol, no matter what we do, if we nanospray dry it, if we lyophilize it, if we add LNPs, if we don't, it always dries in a crystalline form. And this is not as good in stabilizing LNPs as an amorphous matrix would be. But this is probably while we can reach the very, very low temperatures in spray drying. For the amorphous drying sugars, we cannot go to room temperature yet to really achieve a dried powder. So what you have to do here is you really have to think those two things as intertwined. You want a formulation that is really stabilizing our particles, but that can also perform well at a very low or the lowest possible spray drying temperature. What do I want you to learn from today? If you want to establish a nano spray drying process, you have to think about pumping and nebulization. There will be shear stress on your particles, and this can mean that they aggregate and that they release part of their RNA, which then can't work anymore. But you can optimize it. We did it, and it works. The other thing I want you to see is that you really have to think formulation and temperature as interdependent. It is possible that there is a trade-off between the lowest possible temperature and the best LNP stabilization efficiencies. And we hope that in the future, we will find a formulation where we can really optimize this and find, a maximum of stability at a minimum of temperature. With this, I want to thank my supervisors and my colleagues for all the support. And I want to thank you all for your kind attention and for having me today. Thank you very much.
Thanks, Katrin. That was great. I think we've got time just for one question. Do we have any questions from the audience? Yeah, one at the front.
Yes, very, very nice talk. I wanted to ask, what is so the nano spray drying is really very low yield, right? You cannot really scale it, and that's what the manufacturer says, Bucci. What was the concentration that you started with? Is it, I assume it's very diluted, right?
Yes, we actually diluted it quite a bit. So we have 5% of the matrix, and then we use 8 nanogram per microliter, or sometimes even 6 nanogram per microliter of RNA inside of the LNPs and inside of the formulation, because that's also something that we saw in the previous work, that nebulization, the nebulization impact is concentration dependent. The lower the concentration, the lower the impact, seemingly. That's why we didn't want to go very high here. And you're right, this is a problem for the scalability. But right now we're at the point where we want to find out, does it work at all? And for that, we have to try with the best kind of, concentrations and RNA types and everything to make sure that it does work at all and find out if we can use it.
Yeah, very good. And the second question is the inlet temperature. The one that you show is the outlet temperature, I assume.
Yeah, in fact, if I use room temperature, inlet temperature, then the outlet temperature will be also room temperature. I actually showed inlet temperatures. I know that usually for spray drying, outlet temperature is the interesting one. However, in this case, I hope that you can see it here actually. You see that the atomizer is hanging really inside of the airflow. And because we're nebulizing so slow, the feed will sit in the inlet temperature pre-nebulization for a bit of time. So we also have to keep in mind that even the inlet temperature needs to be very, very low here, and not only the outlet temperature is interesting.
Thank you.
Thank you.
Thank you, Katrin. I think in the interest of time, we'll, if anyone's got any further questions, please catch Katrin after or in the break. And thank you again.